Welcome to another video on vector calculus. Today we will be talking about surface area. We've already looked at how to find a volume of a solid using double integration. We've also looked at how to use polar coordinates when we're looking at circles, for example, or other types of shapes that lead themselves well to polar coordinates. So the plan today is we'll be talking about the definition of surface area. We'll start out with that. It shouldn't be too surprising how we're going to start out, and you'll agree with integration, it's always the same story, as we'll see. Then we'll look at how do you calculate surface area. We'll have some examples where we want to find the surface area of a surface that lies above some region in the xy plane. And we'll look at calculating, and then we'll realize that calculations are very challenging. So I'll give you some examples first. You won't notice that they're challenging, and then we'll see that most examples are basically impossible without technology. So we'll use technology, and we'll play around with a computer, and I'm assuming that you know how to use a computer or a calculator to perform a double integral. So let's start out with approximating surface area. So what I have here is this wonderful surface. And what we want to find out is what is the surface area of this wonderful surface. And we've seen the story before. What we do is we look at the xy plane, and we can think about cutting the xy plane into a grid. And I'm going to take one little one of these little rectangles in the xy plane, and I'm going to project that upward. And what I get is a parallelogram on the surface as long as my rectangle is small enough and the function is continuous. So I want to find out what is that area of this parallelogram. So to find that out, I need to find out what are the vectors u and what are the vectors v. So let's investigate a little bit more closely. So notice that u is the projection of the vector delta x, basically I, up onto the surface. So y isn't changing at all. So we'll notice that we can write this in the xz plane. The x coordinate of the end of that vector will just be delta x because we moved along a little delta x amount. And the z coordinate will be delta z. And delta z is approximately equal to f sub x times delta x, where f sub x is the partial derivative of f with respect to x. That's what partial derivatives do. Notice that if I divide by delta x on both sides, I get delta z over delta x is equal to the partial derivative of f with respect to x. Kind of the definition if you take a limit. Also, I'm being a little bit lax. What I really care about is not necessarily this little first rectangle, but any rectangle. But when you subtract, you get delta x and delta z in terms of head to tail. We could do the same thing to find this vector v. And the vector v, now we're taking this little y component with delta y, and we're going to lift this up onto the surface. And what we get is our vector v, which is going to be in the yz plane. Its y component is going to be delta y, because that's what we've done. We've lifted up this delta y upwards. And the z now is going to be f sub y times delta y. Notice again, if we divide left and right by delta y, we get delta z over delta y is equal to del f over del y. And that's basically the definition when you take limits and you have continuous differential functions and all of that stuff. So that will help us find the surface area. The next thing I want to do is I want to find not just what is this parallelogram, but what is the area of this parallelogram. First thing, we could write down the vector u in vector form, delta xi plus f sub x delta xk. And we can write down the v as delta yj plus f sub y delta yk. And we want to find out the area of this parallelogram if we know that the two adjacent sides are u and v. And we've had that. And what we had is that the area of a parallelogram is the magnitude of the cross product of those two adjacent vectors, u cross v. Let's now find the cross product of u and v. To do that, what we need to do is we need to take the determinant of the matrix. And the matrix's first row, as you should know, is I, j, and k. The second row should be the components of the vector u. The I component is delta x, the j component is 0, and the k component is f sub x times delta x. And the third row consists of the components of v. The ith component is 0, the jth component is delta y, and the kth component is f sub y delta y. So now let's find the determinant of this matrix. So to do that, we cancel the top row and the left column, and we get 0 times f sub y delta y minus f sub x delta y, which is just negative f sub x delta y, and that's the ith component, so times I. For the jth component, I cancel out the first row and the middle column, and I get delta x times f sub y delta y minus 0. And notice for the jth component, I need to multiply by negative 1. So I arrive at negative f sub y delta x delta y, and then times j. For the kth component, I cross out the first row and the third column, and I get delta x delta y minus 0. So we just get delta x delta y k. Now let's find the magnitude of this vector. So I just take the square root of the sum of the squares of the components of this vector. So I get the square root of negative f sub x delta y, quantity squared, plus negative f sub y delta y, quantity squared, plus delta x delta y, quantity squared. So notice here that delta x delta y, quantity squared, is in all three of these terms. So I can factor that out and pull that completely outside of the square root. And I arrive at 1 plus f sub x squared plus f sub y squared, the square root of all of that, times delta y delta x. And that gives me the area of one of those parallelograms. Of course, I don't want just one. I want all of the parallelograms. To get all of them, I add them all up. That'll be a double sum because we have a delta x and a delta y. I don't want just an approximation of the surface area. I want the exact surface area. So as you're used to, we're going to take a limit as delta y delta x approaches 0. And what we get is the following definition. And it says, let z equal f of xy be an integrable function over a region R in the xy plane. Then the surface area of the surface z equals f of xy over R is the double integral over the region of the square root of 1 plus fx squared plus fy squared dA. So we found the area of one of the parallelograms. We do the addition of all of them. We take a limit, and that gives us our double integral. So that is the important concept of this entire lesson. And that is that the surface area is the double integral over the region of the square root of 1 plus fx squared plus fy squared times dA. So now all that's left is to apply this to some examples. So here's my first example. It says, find the area of the part of the plane z equals 6 minus 3x minus y that lies above the region in the xy plane, bounded by the curves y equals x squared and y equals x cubed. So as usual, I like to draw a little picture. We have our plane, z equals 6 minus 3x minus y. And then we have our two curves. We have y equals x squared, and then we have y equals x cubed. That gives this little wedge thing. We've seen this in first year calculus, that little wedge before. But now we're lifting that up onto the plane, and we want to find out what is the surface area of that part of the plane. So now the little man comes to our rescue. So there's integral man. It's a happy little guy. And notice that we have the region in the xy plane. That's the important thing for double integrals, not this whole full surface, but what does it look like in the xy plane. And we have the curve y equals x cubed, which is below the curve y equals x squared. So the little man's head is at y equals x squared, and the little man's feet are at y equals x cubed. These curves cross at x equals 0 and x equals 1. So now let's go and use our definition. To do that, we need to take the partial derivative of f with respect to x and y. So that's very simple. The partial derivative with respect to x of 6 minus 3x minus y is just negative 3. And the partial derivative with respect to y of 6 minus 3x minus y is negative 1. It's always nice when they're both constants. It makes life a lot easier because we can put this together and say the surface area is the double integral. Remember, the little man went from 0 out to 1, so 0 to 1. And the feet were at x cubed, and the head were at x squared, so from x cubed to x squared. Then we have the square root of 1 plus fx squared plus fy squared. Notice that negative 3 squared is 9, and negative 1 squared is 1. Then I just do a little arithmetic. 1 plus 9 plus 1 is 11. And then if I take the integral of the square root of 11 dy, square root of 11 is a constant, so the integral of the square root of 11 dy is just a square root of 11 y. And we're plugging in x cubed to x squared dx. So if I plug that in, I get the integral from 0 to 1 of the square root of 11 times x squared minus x cubed dx. That's a very simple integral. The integral of x squared is x cubed over 3. The integral of x cubed is x to the 4th over 4. If you plug in 1, you end up with a third minus a fourth, which is a 12th. If you plug in 0, you just get 0. So our final answer is that this surface area is equal to the square root of 11 divided by 12. And I'm done with the problem. So now let's look at another example. So the next question asks us, find the area of the part of the paraboloid z equals x squared plus y squared that lies below the plane z equals 9. I start out by using a computer to sketch those. Here's our paraboloid. Here's the plane. We get this bowl-looking thing. What really matters is that the intersection of this parabola and the plane is x squared plus y squared equals 9. I just set them equal to each other. And I could put the little man on the figure. This is a circle. X squared plus y squared equals 9. The radius of the circle is 3. There's our little man. But I think I hear him saying something. Do you hear that? Do you hear that, little man? What'd you say? I thought so, but I still can't hear you. Can you speak a little bit louder? Polar, of course. The little man will always help us. When we see a circle, you should always listen to the little man. Circles tell you, think polar coordinates. So this is a problem where we're going to want to use polar coordinates because our region is a circle. Circles are just inherently made for polar coordinates. So now let's go ahead and do the computation we need. Because I want to use polar coordinates, I'm going to wait on the limits of integration and what I call my dA till later. But I do need to plug in the partial derivatives. We can say that the surface area is the double integral over the region of the square root of 1 plus The partial derivative with respect to x is 2x, so we have 2x squared. The partial derivative with respect to y is 2y. We get 2y quantity squared dA. We can simplify that a little bit and say that 2x squared is just 4x squared, and 2y quantity squared is 4y squared. We could pull out that 4, and we could say this is the double integral over the region of the square root of 1 plus 4 times parentheses x squared plus y squared dA. Now we want to use polar coordinates because the little man was screaming at us, use polar coordinates. So we go to polar coordinates. Notice that that x squared plus y squared is also very nice. That becomes just r squared. And what we get is the double integral. The first limits are going from 0 to 2 pi, that's theta. There are no constraints on theta because we're going all the way around the circle. So we go from 0 to 2 pi. The radius goes from 0 to 3. And then we have the square root of 1 plus 4r squared. And then don't forget that in polar coordinates you have an r dr d theta. And this is nice actually because we can use u substitution. So now I can integrate this with u substitution. I could let u equal 1 plus 4r squared. Du is 8r dr. And this is nice because I have the r dr available. So I have to pull out a 1/8. I end up with a u to the 1/2. The integral of u to the 1/2 is 2/3 u to the 3/2. 2/3 times 1/8 is 1/12. So I end up getting the integral from 0 to 2 pi of 1/12 u to the 3/2. If I plug in 0 for r into our u equation, 1 plus 4r squared, I get 1 plus 4 times 0 squared. That's just 1. So there's my 1. If I plug in 3, I get 1 plus 4 times 3 squared. 3 squared is 9, times 4 is 36, plus 1 is 37. My u limits become 1 to 37. Then I have d theta. And I could plug this in. If I plug in 37 and I plug in 1, I just get constants. And the integral of a constant from 0 to 2 pi is just 2 pi times that constant. And I put that in my calculators. It's just some hairy arithmetic. And I got around 117 for this integral. So there is the surface area for the part of the paraboloid z equals x squared plus y squared that lies below the plane z equals 9, and we get about 117. I have one more example to show you that's a little bit more realistic. So the question states, find the area of the part of the surface z equals x squared times e to the 3xy above the part of the ellipse x squared plus 4y squared equals 1 that lies in the first quadrant. As always, I like to use a computer, get a little picture. And here's my picture. I have this beautiful little surface. I have this bit of an ellipse, a quarter ellipse. If I project that upwards, I get this piece of the surface. And I want to find the area of that surface. We don't necessarily have to draw this three-dimensional picture, but it's beautiful and computers can do it pretty easily. What we do need to do, though, is get the help of our little man. So I solve for y in this ellipse. I subtract x squared from both sides, take a square root and divide by 2, and I get y equals 1/2 times the square root of 1 minus x squared. Notice that we're in the first quadrant, so the little man's feet are at 0. The little man's head is at this curve, y equals 1/2 square root of 1 minus x squared. The little man can walk to x equals 0 to the left and walk to the right at x equals 1 on the right. So now let's take a look. I need to find the partial derivative of z with respect to x and with respect to y. To find the partial derivative of z with respect to x, I need the product rule and the chain rule. The derivative of x squared is 2x, and the derivative of e to the 3xy with respect to x is 3y, e to the 3xy. So when I use the product rule, both terms will have an e to the 3xy. I factor that out. And I'm left with a 2x. And then remember, 3y times x squared is 3x squared y. To find the derivative with respect to y, that's a little bit easier. X squared is just a constant, so I can pull the x squared out and find the derivative with respect to y of e to the 3xy. And that's just 3x e to the 3xy. 3x times x squared is 3x cubed. And then times e to the 3xy. Now I can use the definition of surface area and say that the surface area is equal to the integral from 0 to 1, because the little man walks to left to 0 and right to 1. The integral from 0 to 1/2 times the square root of 1 minus x squared. And then comes the square root of 1 plus the square of the x derivative plus the square of the y derivative. Notice that both the x derivative and the y derivative have an e to the 3xy term, and the square of e to the 3xy is e to the 6xy. That's just the power rule for exponents. So I could factor out the e to the 6xy, and then square each of the other two terms. So we have 2x plus 3x squared y, quantity squared, and then 3x cubed quantity squared is 9x to the 6th. And then we have dy dx. And I know maybe you're all really excited about trying to do this integral by hand, but good luck. This is miserable. And in fact, in most examples, I know I showed you two that we could do, but in most examples, the integral is not going to be able to be done by hand without doing some miserable power series, and even then, it's just miserable. So typically, we use a calculator or a computer to evaluate the double integral. And I did that, and I got that this double integral is about equal to 0.62. So I can now say that the area of the surface, z equals x squared, e to the 3xy, that sits above this region is about equal to 0.62. And I'm done with the problem, and that's the last example I have to show y'all. So hopefully you understood how to find surface areas given a surface and a region. If not, feel free to ask me some questions, or if you have a different instructor, feel free to ask your other instructor questions about how to find surface area. Have a wonderful evening or day or morning or whatever time it is for you, and thank you again for watching this video.